No worries. Hey, Greg.
Hey. All right. um, Kent, any updates?
Hello.
Hey.
So yes, so the week started with a so there was a discussion of whether we should switch from explicit peak to implicit peak. And specifically what this means is that for explicit peak, there would be a special syntax symbol required for the so-called peak action in Rowline, which would read from a channel and put whatever was at that channel back. And that action, it doesn't change what's at the tuple space. So it should, in theory, be something that is mergeable. And the implicit version of that is, or we could do that implicitly in the sense that if we just happen to take and put back a value that was the same as it was originally at a certain channel, then we could treat it as a peaking action. And
I'm sorry, I don't understand. Can you say that again?
It's what we discussed last Monday,
No, I know, but the way you described it just now wasn't clear.
I see.
I mean, the model that the R space is built on is the special K model that I devised, I don't know, over a decade ago now. And the whole point is that you recover all these distributed systems programming paradigms or conventions if you recognize that there are two things you store in the tuple space, and only two things. You store data and you store continuations, and you maintain the law of excluded middle in the database, which means at a given name there's only three possibilities. Either there's a continuation stored there, there's data stored there, or there, the name hasn't been used in the tuple space before. And then you have a table which is whether or not when a continuation meets a name, what happens with respect to either of those, so that you have two possibilities, persisted and ephemeral, right? And the read or the peak corresponds to when the continuation is ephemeral but the data is persisted. And I had always we have planned for all four of those operations to be made available via the tuple space. So an explicit peak is a natural thing that arises out of the design. and should therefore be made. And if you go look at the Rolang 0.1 spec, it points out all the syntax for each of those different possibilities. So we should have that available. Now, what is the implicit idea, for our listeners, and why is it good or useful?
So the implicit peak, the idea is that you will take from a channel, and if you put back what you take, then it would be considered a peaking action.
Sure. Right, but the point is, why do we? I mean, you could always do that before, right? You can always simulate read in Rolang by taking the value and putting it back.
Yes, that is you're describing the explicit peak, right?
No, I'm describing the implicit peak.
Okay. Yes. And so yeah, the discussion, as you know, is about whether it makes sense to just switch to just having a implicit peak, and we ultimately put that on hold.
Right. Yeah. Exactly. Yeah.
Okay. Yeah, I just wanted to point out that we had that discussion. So the other thing was that we worked on removing volatile produces and consumes. And so what a volatile produce or consume is one that essentially it's something that ends up not, it's a producer consume that ends up not affecting the try. And so let's say you have something simple like a send on a certain channel and a read from that same channel within the same block. And the continuation of the read is simply nil. Then the net effect of that send and read is nil because of how they reduce, and then the continuation is executed and it's just nil. So the produce and consume in the example I gave is it's they're both volatile, and so we can safely allow any block that contains volatile produces and consumes only to be removed. And not only that, but we can remove any volatile producing consume from the set of channels that have been touched in a block. And when we compare whether a block is mergeable against another one, we can do that the same thing for all the blocks involved, and execute the merge based on whether the set of channels used intersect once you've subtracted the volatile produces and consumes. And this is a PR that is in the works.
Cool. So you haven't submitted it yet, right? It's still underway.
Oh no, the PR is up.
Oh, okay. So it's being reviewed now.
Yes.
Awesome. That's really cool. Yeah, for people who don't know, the a part of the advantage of having Rho as the execution mechanism means that we can detect conflict, and because essentially the only time conflict can occur is if you have two different transactions touching the same name. But not all of those situations even are necessarily conflict. So, for example, if you have two writes or two reads, those are not in conflict. And we can analyze a lot more situations than just those to figure out when it's possible to go ahead and include transactions because they don't actually conflict. And all of this arises from the structure of the execution mechanism. And when we have that, the more transactions we can include in a block, the effective throughput goes up, as long as the calculation to do the merger of certain blocks doesn't cost too much. If the overhead of doing the merge versus the improvement that in throughput that you get, that's the ratio you have to look at, is the overhead of doing the merge versus the improvement in the throughput. In principle, it should be the case that you can dramatically increase throughput, but in practice you have to be careful to look at what the actual overhead is. So it might be the case that the way the merger is calculated is expensive in one way or another, or there's some complexity there. And so you have to be careful to be efficient in the block merge calculation in order to get the best improvement in throughput. Awesome. Anything else?
Nope, that concludes my updates.
Awesome. Thank you, Kent. I really appreciate it. So I'm busy writing up the square root stuff. The one thing I noticed as I've been writing this up is that if you don't focus on the how do I explain this? If you don't focus on using the annihilation style rule, and you just look at what's necessary as a process to ensure that all copies of a particular tangle choose the same winner, then it appears that you must have a mixed summation process. Like the smallest way to express it, the process that you interpose to get the all of the tangles to agree on the winners of the race. That looks like it's mixed summation, which is very, very interesting. because it's known that mixed summation doesn't or has greater expressivity than input guarded summation. So there's a paper by Katusha Palamadisi that shows that there's no par preserving translation of um, mixed summation uh, down into the asynchronous pi calculus, and these results extend to the row calculus. So there's an interesting issue there um, that suggests that consensus is strictly more expressive. That when you add in consensus in this way, you're adding in something that is strictly more expressive than pure asynchronous calculus. And this makes sense, right? Because you can't have um, uh, consensus like this in a purely asynchronous setting, right? So basically, as soon as you have any sort of consensus that works, you have to impose some kind of synchrony constraint, uh, or you run into FLP impossibility. So this is extremely nice because the mathematics is, I mean, we're the mathematics is lining up very, very well. All of the results that we know are sort of fitting together in a way that that it, I mean, like to the best of my knowledge, like Palamadisi never looked at the consequences of her results with respect to, or what they mean about distributed consensus. But they say something about distributed consensus, and what they say about the expressivity of the calculus is directly connected with um, what we know about FLP impossibility, right? So without some extra thing, you can't overcome FLP impossibility. So that's what's showing up now in this calculation, and it's very, very pleasant. I mean, this is exactly what we want. So so this is how do I say this? So we have this nice crisp idea, what's the square root of a process, and to calculate that, you end up when you calculate that, you end up with uh, having to find a process that when interposed with a bunch of copies of tangles, where these tangles are essentially, the minimal fragment of your process that is involved in a race. So you get a bunch of copies of these tangles, and you have to interpose with that something that makes all of them agree on the winner of the race. And that thing that does that, the smallest form of that is a mixed summation, and mixed summation is strictly more expressive than async pi calculus, right? Or the way to say it is there's no par preserving translation. Since they're both Turing complete, you have to be able to encode one and the other, but the lack of par preservation means that you're doing extra work, and that extra work is the synchrony constraints. That's precisely what it is. So this is turning out to be a really, really fruitful area of investigation. I don't know if any of that made sense. Kent, did you follow?
So I guess I'm confused how the so first of all, when you say par preserving, you mean the the fact that the par is not ordered with respect to com events.
So a par preserving translation is easy to express mathematically. So so our source calculus is a calculus that has mixed summation, which means that you can write a choice um, expression that involves both input and output. So so it's going to stay in so a choice that involves both input and output is going to stay in suspension, either providing an output or receiving an input, depending upon what its environment does with it. And the only way for an environment to interact with such an expression is if you put it in par. But so that's where the par stuff comes in. But so we're building a function that goes from a source calculus to a target calculus. That's our translation function, and it goes from a calculus that includes mixed summation expressions to a calculus that is purely asynchronous. And we know that both of them are Turing complete, right? And so when we put constraints on the translation function, it's showing higher levels of expressivity. So par preserving says that if I have an expression of the form p par q in my source calculus, and I take the translation of that, that has to be equal to the translation of p par the translation of q. Does that make sense?
Yeah, that last part does.
And so when you say that it's not par preserving, that means that you can construct an expression in this source calculus that such that when you translate the expression and you translate the the par, you do it, so you're going to have some process p par q in the source calculus, and you look at the translation of that, and then you look at the translation of um, p par the translation of q, that those two processes are not going to be bisimilar in and have the translation be faithful. So you can either they're going to be bisimilar, but then the translation can't capture the mixed summation, or the translation captures the mixed summation, but then those two processes are not bisimilar. That's what it means, is that there's no par preserving translation.
I see.
Yeah, and this corresponds exactly. So what's slowly emerging from these calculations is that this is exactly um, where the distributed consensus power emerges. And one of the interesting things is that Katusha's proof involves an expression of leader election. So there is some, already in her paper, there is some, hint that this fact it has to do with distributed consensus.
So I guess I'm still not clear what the connection is between par preserving and FLP.
Right. So the so the thing that Palomedisi proves is that when you have mixed summation, that language feature is strictly more expressive than the asynchronous version. And but what does it mean to be strictly more expressive? Right? When both calculi are Turing complete, right? Well, what is expressivity in that setting? And the notion of expressivity here is whether or not you preserve certain features during the translation process. So in particular, the question is, do you preserve par during the translation process? So the connection is, are we so in order to write down this process that is going to have everyone agree on the winner of the race, we need mixed summation. And, or at least as near as I can tell, I can't come up, I don't have a proof that mixed summation is the only way to do it, but what I can say is it's the smallest way to do it. So I in order to be elegant, I need a mixed summation feature in the language to write down this thing that gets agreement across the winners of the race. And mixed summation means that the calculus I'm writing in is strictly more expressive than a purely asynchronous calculus, right? And the purely asynchronous setting is the one where we know that FLP impossibility occurs.
I see. So I guess, is it accurate to say that mixed summation would, well, so it doesn't imply par preserving, and therefore it will be hard to get an ordering of events?
No, well, I mean, that might be the case, but what it's saying is that mixed summation is another way to express these synchrony constraints. In order to overcome FLP impossibility, you have to have some kind of synchrony constraint, right? And we, recently I gave a pretty strong argument, and I basically recapitulated an argument given about 10 years ago that, or I transported an argument given 10 years ago that error correcting codes correspond to these synchrony constraints, right? And so, I was able to show that idea can easily be transported over into the process calculus setting. So no big surprise, right? Process calculi are Turing complete, then anything we can code up there. But it's nice, like when you do code it up there, then you get a lot of interesting things falling out as a result of that. But the big the thing that's showing up here is, I just want to write down the smallest process that's going to get the agreement in the winners of the race, and that uses mixed summation, and that it is another way to impose these synchrony constraints on in the asynchronous setting, right? Like if we're gonna like translate this down to some minimal row calculus process where we we don't avail ourselves of a lot of bells and whistles that we haven't explained, right? Then when we do the mixed summation, it's that is adding the synchrony constraints, and those synchrony constraints can't be par preserving, right? That's the idea. So whatever you're doing in this higher level language, it can't be par preserving, um, and that's because you're adding some synchrony. You're adding some constraints about things that have to be happening at the same time. So that can't be par preserving. Maybe that's the way to think about it. Does that help?
Yeah, it helps a little. I think that, yeah, it's there's no notion of grouping, maybe is.
Yeah. There's no what runs in parallel in one world is not necessarily running in parallel in the lower world, right? Because in the lower world, you can see kind of you can see more about the apparatus that's necessary to get things to converge, right? In the lower world, the world that has less bells and whistles, I don't know how to describe it, a more fine grained world, right? That world is um, it's purely asynchronous, and so whatever you do to ensure that there's some convergence on the consensus algorithm is going to mean that you've added this notion of boxing, right? You sort of you have to box things up so that they're constrained to happen at the same time, or you know um, I mean, it's also closely related to this notion of space-like versus time-like distances, right? So you're saying that you're essentially saying that we put stuff in a we've put stuff into light cones in such a way that we can say things about causality that we couldn't say before. Right. That's essentially what's happening with distributed consensus. When you overcome FLP impossibility, you have more causal information. Right. That's the real nub of the thing. You like FLP impossibility occurs because you don't have enough causal information to to um, uh, to prevent the bifurcation of the network, right? They can never propagate the causal information fast enough to get agreement. That's really what's going on, um, and uh, it, and so if you've overcome it, then what you've said is that there are these boxes or these containers, these light cones, where you can propagate the causal information fast enough to get convergence. So it means that either there's some bound on the time to communicate, or there's some bound on there's some other kind of bound with respect to communicate. It'll be a space-like bound as opposed to a time-like bound, right? So you're bounding the number of channels that you have to use, and that's where the error correcting codes come in. You bound the amount of space you need in order to calculate the synchronization information. Um, Right. So in the case of the error correcting codes, well, it's essentially that you're putting a total bound on computation in order to get this across, and that has to do with uh, and by getting it across, I mean getting it from one side of the network to the other, and again that has to do with the fact that space and time in this setting are inextricably linked, right? So in the physics world, you have this notion of space time, and over in this other world, we know that there's always this trade-off in complexity theory between time and space, right? So you know if you bound if you find some hack that bounds time, then that typically means you have a growth in the amount of memory that you're utilizing. or the other way around. And in this case, that corresponds to the number of fresh channels that you use. The other way around, let's say you want to conserve on memory or the number of fresh channels that you use, then that typically means you have more computational steps. In other words, there's more total time that's taken. So in whether you're looking at it from physics or from information processing / compute, the issue is that these kinds of problems, you can't untangle space from time. They're directly connected, and because of that, when you put these synchrony bounds, you put these light cones around the causal information, then what that says is, any time-like bound, like insisting that you have some bound on message propagation, can be converted into a corresponding bound on the amount of computation it requires, the amount of space, the amount of channels used in order to propagate that information. So, at a conceptual level, that's really what's going on underneath. And so you've got this world where you have mixed summation and the light cones look a certain way. But then when you translate those light cones down into a world where you don't have these synchrony constraints at the syntactic level, then the light cones have to be rejiggered. And rejiggering the light cones is exactly par preservation. Does that make sense?
So I guess what sort of I have a hard time wrapping my head around is, like, I'm used to thinking of, I guess, getting a deterministic order over, I guess, the comm events. That process is done at a separate layer than resolving FLP. And so I guess I'm having a trouble sort of, I guess, merging those two layers together. And I like, I guess when you say, yeah, I'm not sure.
So
Um,
so so
hmm,
we do agree that there are going to be some comm events that are not ordered, right?
yes,
Okay, good. So there's some kind of graph or tree that represents the causal information with respect to comm events.
yes,
Okay, and so you can imagine comm events in a calculus where you have mixed summation. Okay, and those comm events are going to be different, right? Because when you put an expression that has a mixed modality summation in par with another expression that has a mixed modality summation, right, a lot of magic happens, right? Because they're they're choosing the modalities. Like one is going to choose the input side, the other one is going to choose the output side. So there's lots and lots of communication that's happening to make that happen. So when you translate that down into a calculus that doesn't have this mixed modality summation, um, the what we're saying is that the causal ordering on the um and on your source graph is not cannot preserve the cannot be preserved um in the one uh in the target graph. And that's because you have this par between these two mixed summation things, and that par, um the idea that they're independent is a fiction, because there's a traffic cop that's that's directing things, but across those two pars, that chooses which, modality goes with which, IO event.
Yes, that part makes a lot of sense.
Yeah. Okay. Cool. So that's why it can't be par preserving. And what I'm noticing is that apparatus is exactly what overcomes FLP impossibility.
Yeah, I guess. So I understand that the modalities essentially do more work, but is there is I guess, would you be willing to explain how the modalities do the work to resolve FLP?
Yes, that part is the easy part, because those are the things that are deciding the winners of the race. So they're adding extra constraints, from the perspective of FLP impossibility. All we're saying is that we have enough information so that everybody agrees on the winners of the race. When everybody agrees on the winners of the race, you can't have the bifurcation in the network.
I guess that is where I'm confused. What I guess I don't see the connection between the winner of the race and
Well, FLP happens because neither side agrees on the winner of the race. I mean, that's really what's going on, right?
that
So
is
they keep disagreeing.
yes, but that is an effect, if that makes sense, not the that's not the cause of the disagreement, if that makes sense. But maybe I'm just not
It's the fact that the causal information doesn't propagate. And when you have this means by which you can propagate the causal information, that's overcoming FLP. FLP says, I can't propagate this causal information. The two sides of the network keep, just missing each other because we don't have any sort of ability to propagate the causal information.
I see. Yeah, that's a pretty interesting perspective. I never this modality is essentially able to, if such a thing existed, it would be like a over the network modality, or
That's
not
right.
call it. Yeah.
That's exactly right. That's precisely it. And in fact, this point has been raised over and over and over again when we compare the pi calculus with the ambient calculus, because there doesn't exist or no one has ever found, it hasn't been proven, but no one has ever found a fully abstract encoding of the ambient calculus into the pi calculus. So fully abstract would be par preserving. The argument is that ambient calculus is not a good calculus to run over the network, precisely because it does this kind of stuff. It's like you can do leader election in one line and that kind of thing with the ambient calculus. And this is the whole idea, is that certain calculi have a good, because of their expressivity, they match a network like the World Wide Web. So the asynchronous pi calculus, because of its level of expressivity, kind of matches the World Wide Web better than other calculi, like, you know, mixed summation pi calculus or ambient calculus or things like that. Yeah, that's it. That is exactly the idea.
I see.
And so when we're building something like Casper, you know, having the right level calculus for the implementation, and then another calculus for writing down protocols on top of that, you know, on top of the machinery that you're providing to the programmer, is a really, really important thing, right? Being able to say, all right, well, when we're giving Roland to programmers, they're programming essentially at a calculus that runs across the network, right? And we want to be able to make sure that that lands nicely or smoothly onto a calculus that fits the network.
Yes, yes.
And Greg, the calculus that fits the network, would that be the ambient calculus?
No. It's the other way around. The ambient calculus is higher level than the, you know, most common rollouts of the World Wide Web or the internet or whatever you want to call it.
Okay.
Yeah. So it's a lot more expressive, which means that you're going to have to build these super fancy servers, you know, like the nodes that we've got, that are, you know, doing this other, you know, semantic layer.
And another question I was thinking is, so with the work that you're doing on the square root, you referenced the annihilation work that you were doing, and wasn't that in for working on the rate of the throughput of the network? That's how I'm trying to put everything into a context. So this all kind of comes back to the rate.
So the argument is that annihilation gives you a way to program rates. It's not so much that you know, I'm trying to add rates. In some real sense, you know, the implementation that we provided is a stochastic implementation of the row calculus, because the market effectively gives rates to the computations, right? Because we bounded every single COM event by flow, right? You can't run a COM event without having flow. So so then the market determines how much flow is available. So think about, if you think about this like chemistry, right? Then the COM events are two molecules interacting, and flow is the catalyst that allows them to interact. The availability of the flow corresponds precisely to a notion of rate, right? And so the question is, how, you know, can you program that in another way? So that's a pretty complicated mechanism for programming rates. And it's at least as complicated as using the stochastic formulation. And in particular, if you try to do a compositional stochastic formulation, then the math is really complicated. You know, and I just point to Cardelli and Madare's paper to prove my point. That the math is but with the annihilation rule is really simple, is the argument, and it's something that, you know, with the right, you know, like a 14-year-old with a little bit of exposure, a 14-year-old can wrap their brain around the annihilation rule, and whereas it's a very exceptional 14-year-old that can handle all the probability theory for the other one. So the argument is like, can I program rates? Can I think about the way we're programming rates in the implementation of Casper and you know, our chain that is conceptually simpler, and that's where the annihilation provides a bunch of tools for thinking about it in a more simple fashion. And when I do the same thing for this consensus problem, you know, when I try to encode it or represent it in the annihilation setting, it's a way of reducing the complexity of the problem. That's what it's about. Now, I don't know. I mean, it could be that that organizing our code to use the annihilation rule might turn out to be the right way to do things. I don't know yet. I'm not at a point where I'm willing to put that position forward. But what I can say is, you know, in terms of the total amount of tools necessary, it's an order of magnitude less complicated than what we've got, right? Because right now we've got these programmers, you know, slinging Scala sometimes and slinging Rolang at other times. But I noticed that it's 8:01 and I've got to jump over to Developer Standup.
Well, thank you, Greg. That was enlightening.
Oh, well, likewise, I appreciate the opportunity to explain.
Very good. Thank you. Yep. Thank you, everybody.
Ciao.